Okay. Hello guys, a very good evening. Just give me one more minute so that I'll just download it. Just give me one second. Oh, but in this they have given me Google Slides. What should I insert audio? How do you write in this? Oh no. How do I write in this? There is no draw option. I will just check whether I can open this in PPT. Okay, it's coming. Let me share my screen. Right. What happened? Yeah. Okay. So you wrote test on this chapter only, right? Alcohol ethers phenols. Oh, okay. This is your revision, right? Okay. Fine. Fine. Next, first question. In but 3N2 all, the OH group is attached to a dash carbon atom. Now let us write a structure first. Let me just draw. Right. So let us write but. Okay. So we have 4 carbon atoms. Right, we have C, 4 carbon atoms. In the second carbon atom, no, sorry, in the second carbon atom, right, in the second carbon, where is it? Okay, right. In the second carbon atom, we have a double bond, right? And in the, sorry, third carbon atom, we have a double bond. What do you mean with third carbon atom? Okay, let us draw. Right? Say in the second carbon atom, we have a OH, and in the third carbon atom, we have a double bond. That's what we understand. Right? We understand that whenever we have a C single bond C, then a double bond C, and this to this single bond C, any functional group is attached, we call these kind of compounds as allyl group. Like this C double bond C, C single bond C, this group is there. It's called an allyl group. Right? So this carbon, this OH, which you are seeing here, right, is actually an allyl carbon, right? And you understand that that allyl carbon is not primary. Now we know what is primary, secondary, tertiary. Primary is that particular carbon attached to which, how many other carbon atoms? Here you see that this particular, okay, this particular carbon atom is attached to this one as well as this one. So it is going to be a secondary carbon atom. So it is going to be secondary allylic, should be the answer to this question, right? Okay, next. Okay, we have this particular molecule and we are putting K2Cr2O7, right? So K2Cr2O7 is going to oxidize, right? And one more thing, what will happen is we are heating it also, right? Why is it little clumsy today? Just give me 1 second. Okay, fine. So now is it writing? Okay, fine. So yeah, now you're saying that this is containing two COOH groups, right? Now two COOH group on the same carbon atom is a little unstable, right? And if you know that if I heat it, generally, if I have acid and if I heat it, right, you can understand that two things can happen. One is the formation of anhydride, that is removal of H2O, right? The another one is actually decarboxylation, right? All that you have to do is remove some CO2. Okay, so let us write the structure of this molecule. Right, we have an OH, right, and then we have a COOH, another COOH, and we have to remove CO2. That is what is decarboxylation, right? Now decarboxylation. Let us remove CO2. Say if I remove one CO2 from this, okay, basically one CO2 from this, and this H is also gone, right? So understand that there's going to be only one COOH present in this molecule, right? For sure, we are going to have only one COOH present because another carbon is going out as CO2. That is decarboxylation, right? Now the next one is this OH is there, and we are putting a strong oxidizing agents like K2Cr2 and potassium dichromate. Right now, what will happen to alcohol? Alcohol will get oxidized to form C double bond O. Right? So the answer for this question will be what? B will be the answer for this question. Right? Okay. Next. The major product of the following reaction is, now we are having C double bond COOCH3 means what? We are having CH3, CH double bond CH, COOCH3 means it's an ester. C double bond OCH3. This is what we have. Right? Now, if I know if I put LiAlH4, this double bond will not be touched by LiAlH4 as well as NaBH4. NaBH4 also will not touch your C double bond. They will not reduce those bonds. They'll only reduce what? They'll only reduce your C double bonds. Right? And esters will be reduced to what? To aldehydes. That's what will happen. Now, I think it will even go to your alcohol. So you'll form CH3, CH double bond CH. Now, this entire thing, right? This will be gone. This will be gone. And this entire thing will become CH2OH. That's it. This entire thing becomes CH2OH. That's what will happen. Right? So where is it? So it should be D. CH3, CH double bond CH. Now, double bond will not be touched by the LiLH4, and your ester will get reduced to alcohol because LiLH4 is a strong reducing agent. Right? We know that. Fine. Next. Arrange the following alkanols 1, 2, 3 in the order of the reactivity towards your catalyzed dehydration. Now, you have to understand how the mechanism works, right? So what happens here, for example, if I have CH3, CH2OH, right? Now we are going for acid catalyzed dehydration. That means first H plus comes. This H plus will be taking up the lone pair on this hydrogen. I mean, this lone pair will take up this hydrogen, forming CH3, CH2, OH2. Already it has one hydrogen, one more hydrogen will come, but now in this case, oxygen will have a positive charge, right? Then what will happen? Now the elimination of water molecule happens, H2O. This molecule is H2O, right? Now you have to show the bond cleavage also very nicely. You are going to break this bond, whatever I'm highlighting, becoming dark, right? I'm going to break it and give it to oxygen so that this plus charge on oxygen will be gone and it will be able to go out as H2O, right? Okay. So if I do minus H2O, now obviously this carbon atom is losing electrons then, isn't it? If I donate both the electrons to oxygen, carbon atom is losing electrons. So you are going to form CH3, CH2 plus. All we understand is we are getting a carbocation, right? So this particular alcohol will be very highly reactive if I can form a very, very stable carbocation. That is what you have to understand, right? So in this case, if I just remove the OH and put a carbocation, that's all you need to do. This is the carbocation here. This is the carbocation here. This is the carbocation here. Okay, right. Now this is a primary carbocation, right? There is only one carbon atom. And this one, oh, there are two OH groups. This is one OH and this is also OH. Fine, no issues. Now this anyway is going to be a tertiary one. Right, this is tertiary. And then you understand that this one is attached to one carbon. Say when I say CH3 twice, what do you understand? You understand that it is going to be CH3, CH, CH3. This is what you mean by CCH3 twice. This is also tertiary, right? Okay, fine. Then in this case, both are tertiary and this one is primary. Then how do we decide?
Sir,
yeah.
Sir, I have a doubt.
Yeah.
Sir, in the third one, like the carbon is attached to 5 atoms.
5 atoms. That is, no, it's C is there, one H, two CH3s, and one CH.
The question, sir, like So
What color?
third subdivision. So you darken the alcohol, right? So 2 times methyl and 1 alcohol.
Oh, understood, understood. I think there should not be any H, I guess. Right? There should not be any H on this compound. This H should not be there. That's what I think they're a mistake. Okay, fine. So anyways, so you would have formed a tertiary carbocation then anyways. Okay. Now tertiary carbocation both cases, but in this case you're forming a primary. And then anything will happen with the help of this OH. Oh, like that. Mhm. Okay, guys, I don't know why are they giving me these questions. This is something called as neighboring group participation. Okay. See, we are talking about this, the stability of this particular carbocation is getting formed, right? If I can just show you in the previous page, let us take this molecule, second one. Say we have CH3, CH plus, that's what we have, right? Oh, sorry. Right, CH3,
Sir,
CH, yeah, tell me, come on.
sir, could you please erase the pen marks on the molecules?
Yeah, sure, that I can do. Yeah. Okay, now this is what I have, right? All I have to do is remove the OH and put a carbocation there, right? Let us put the carbocations alone. So this will have, oh, sorry. So this will have a primary, this will have a primary, and this will be a tertiary, and then this will be a tertiary again. Okay, right. Both of them are tertiary. Now we have to decide. That's why I said I'll just go to the previous one. Okay, so we have CH3, CH plus. Say there's no hydrogen here actually. There is one CH3, and then there is one CH3, CH2OH. This is the second molecule. Okay, it has OH, and other one is going to be just CH3. Okay, right. This is CH2. Okay, right. Now, what you understand is this negative, this positive charge is going to be stabilized by this carbon, this carbon, this carbon, in even the third molecule also, right? But because of the presence of this OH, something else is going to happen. Extra is going to happen in this molecule. And what is going to happen, do you think? Now, you see that there's a lone pair on this oxygen. Is it not? Now, this lone pair can be donated to this carbon, so the carbon does not have a positive charge. So positive is decreasing. Now, this is what is your neighboring group participation. This does not actually take part, actually, this carbon, this thing will not change, right? But the thing is that it is somehow going to help in the mechanism, right? If you want to understand how this works, say now you're seeing that 1, 2, 3, 4. Right? Along with oxygen, if this oxygen makes a bond with this carbon, it is going to make a 4-membered ring, right? We will make a 4-membered ring along with oxygen first. Okay, and in this one, oxygen is having a positive charge. Okay, right. And that oxygen is attached to one carbon. Okay, let's say it can be any carbon. This carbon we will take, and that carbon is attached to 2 methyl groups. 1 methyl group, 2 second methyl group. Right. Anyways, now this is not going to be a stable structure, but still what you understand is this, because of the presence of this OH, this is actually stabilizing this positive charge. Is it not? Right. So because of that, definitely the second one will be more stable. The carbocation found by the second one will be more stable. So second one should be more reactive. So the answer should be Yakana.
Sir, why there is no hydrate shift?
We can do hydrate shift, yes.
So,
but why will you go for hydrate shift? No. The first question is, why will we go for hydrate shift if we already have, what is that? Your OH in the tertiary position. Are you able to understand? Even if we go by that logic, okay, we'll go by hydrate shift logic. Okay. So here what I understand is there is one OH, right? And here also the same OH tertiary position. We don't have to do anything, right? But say this primary, if I shift one hydride from this, the positive comes here. If I shift one, methyl group, okay, if there's no hydrogen also, isn't it? 1, 2, 3, 4. Yeah, hydrogen also not there. Yeah, we can maximum form a secondary carbocation only. Right? Okay, that logic also doesn't work. Right? Here, here it doesn't matter. Right? If at all you're able to form a tertiary out of something, then that makes sense. Right? Primary to secondary also, sometimes we cannot do hydrate shift or alkyl shift.
Sir, so in the first case, won't there be any hydrate shift?
Sir,
First case. First case, yes, there can be a high redshift, absolutely. So now you see that this will happen here. So we'll have a positive charge here. And now the hydrogen shifts here, the positive charge comes here. Now you're forming a tertiary. Yes. So here high redshift would happen and makes it into tertiary, but still the answer will not change. All of them are tertiary now. Right? Okay.
Yes, sir. So all
sir.
of them are okay.
Yeah, we'll finish. What is that for? What is it?
Yes. So all of them are tertiary, sir. So like,
Okay.
how will you arrange them in terms of stability now in this case?
That's what. So that's what. So here, what you understand is this one I told you is going to be the most stable one, second one, because of this OH, right? Because of this lone pair getting donatized. Did you understand that? This one, what we wrote here, I have a OH attacking this carbon, right, and forming a stable structure. Right, it is more stabilized, this positive, this tertiary. So that is the second one, right? But when you go to the third one, right, there is tertiary here, and there is the same thing actually is here if you go for high redshift, right? And then you see that, but in this case, the given molecule is at least is primary, right? This primary has to change into tertiary, but this is already tertiary, so we can conclude that this will definitely be more stable than this. So 2, 3, 1 will still be the answer. D will still be the answer.
Okay.
Yes. Suprajit.
Sir, but in second structure, how can hydrate shift happen from tertiary to secondary, sir?
No. We're not talking about hydrate shift. It's all about this one, this OH, which is there in the tertiary position. Right?
So
That
hydrate
is
shift won't happen, no. So the positive charge would still stay on that carbon. Right?
Yes. In this case, no hydrate shift. In the second molecule, there's no hydrate shift. In the third molecule, there's no hydrate shift. But in first molecule, you will be able to convert a primary into tertiary by hydrate shift. So that time it's okay. That's what you're telling.
Okay, sir. Understood. Sir.
Okay. Moving on. Guys, 1 second. Okay, right. So this question, which is the following, has maximum pKa value. Now, all you understand is Ka is directly proportional to the acidic strength, right? And this is going to be inversely proportional to the pKa. That means higher the pKa value, lower the acidic strength, right? So in case if they ask you pKa, you have to arrange them first in the case of acidic order, acidic strength order, and then reverse it. That's the best way to go about it. Okay. Right. Now, again, how do we check for why are we even talking about acidic? How do we talk about acidic strength here? That's very simple. The acidic strength, right, is directly proportional to the stability of the conjugate base. The stability of the conjugate base. We know what is the conjugate base. After removing H plus, whatever is remaining is what is called as the conjugate base. Right? That H plus you remove and you check for what is remaining and its stability. Whichever out of that conjugate base is the most stable, that is going to be maximum acidity. Okay. So if that's the case, let us go here. Right? I'll just remove all the hydrogens from this. Right? And put a O minus, O minus, O minus, and O minus. Right? Now, stability, how do we check? With respect to charges, lesser charge, more stability. That's how we check. Is it not? More and more towards neutrality it is, more and more stable it is. Right? So here we see that there are electron donating groups this side, and this side, which is increasing this negative charge. Right? And this side I have only 1 increasing the negative charge. This side I have 2 increasing the negative charge, and this side also I have only one increasing the negative charge. Is it not? Because all alkyl groups are electron donating in nature. We know that. Is it not? All your alkyl groups are electron donating in nature, and they will increase the negative charge on the oxygen by donating more and more electrons towards it. Okay, right. And if that's the case, can we say that this one is going to be the least stable one? For sure, because it is having the highest amount of negatives, because three of them are donating here, right? And I can say that the minimum is definitely going to be for either this or this, because only one side it is coming, right? But all that I understand is bigger the group, bigger the electron donating power, right? Electron donating power of this is higher because this group is bigger than this group, whatever I have here. Right. So here the negative charge increase comes here. For example, if it is this much, here the negative charge increase only will be this much because of the group difference. Right. So that I can say that this is the greatest, or this is the most stable one. That is option D. Right. So now they're asking us about which is having the maximum pKa. That means they're asking about minimum acidic strength. The least acidic will be the least stable one, and the answer would be A. If they ask you the minimum pKa, then the answer would have been this, D. Okay, I hope everybody was following. This question was really important. This will be applying for your carboxylic acids also. Same concept, exactly same concept. Okay. Right. Moving on. The compound which reacts fastest with Lucas reagent under at room temperature is, again, we know the order of reactivity. In case of your Lucas test is tertiary alcohols will react the fastest. They'll form turbidity immediately. And then your secondary alcohols will form after 5 minutes, and then your primary alcohols will form only after heating. Right? They form faster. That means talking for a tertiary alcohol is what we understand. Right? Now, just you'll go for here propan 2, all 3 carbon atoms. So the second carbon atom having OH, and your 2 methyl, second carbon atom having methyl. Yes, this is tertiary, definitely. Okay. Next, propan 1 all, that is CCC, and 1 OH in the first carbon atom, and second atom is a methyl group. This is secondary. Right? Okay. Butan 1 all will be primary for sure. Butan 2 all will again be secondary. Right? Obviously, only the tertiary one here is option A. Right? Moving on. The major product of the following reaction is RCH2OH, anhydrous, and a carbocation. H plus anhydrous. What reaction is this? Or CH2O minus also, if I take, and that attacks here, and this goes here. Or I think I have to break any one of the sigma bonds only. So if I take this, what do you mean by H plus also? Chalo, no issues. So say H plus takes up this H, right? And then you'll form OH plus. And then this comes and attacks here. This bond goes here, and this bond goes to this. So in that case, you will be forming this one carbon atom. If I start with that carbon atom is CH2. No, CH double bond OH plus, and this one is attached to this one, that is CH, and that is having OCH2R. And then we have this one, CH2, CH2, CH2. Okay. Yeah, CH2, CH2, CH3. Right? Okay. So to remove the positive charge, all that I want is removal of H plus and donate the electron back to this. So then I'll get a CHO, CH. So next carbon atom is having an ether only. Ether. Yes, answer would be an ether. Okay, guys, this is definitely not part of your syllabus, but still we can find the answer if you think smartly about this. Okay. I don't know why are they giving questions like this. Okay. So first we'll take up the H plus, right? एक no, total चार बना दो, तो चार उठा लो। दो मेरे को दो। Okay, right. So this will take up this H plus, right? So in that process, it will become OH plus, right? Then what happens is this becomes a very good site for nucleophilic attack, right? Let me make a page and explain. Right. So we have a double bond here and O, and this is having a positive charge. Now what happens? This RCH2OH, say I will take the nucleophile RCH2O minus, and this will attack here. And in this process, this will go here. And in this process, this bond will break. Okay, right? So what will happen is that if I start with this one, it is actually going to form CH2 minus, one more CH2, one more CH2, one more CH2. Right? And then I have this. Now it's not a CH2 actually. Now this is going to contain this one, right? So it should be CH2, means CHO, CH2R, whatever is there, right? And then what is happening? Now I have the next carbon atom. Between that, I have a double bond now, isn't it? No, double bond is broken, right? Single bond. Now comes this carbon, where that is having a double bond O with this oxygen, and that is having a positive charge with hydrogen. That's what you understand. Right? And then for this, I think there's one more hydrogen present. Yes, that's not an issue. Okay, right. Now what has to happen? Now you see that this is having a positive charge. If I can just remove this positive somehow, then that is very easy. Break the bond like this. It is going to become O minus, that is going to cancel this, and H plus comes out, and that H plus you'll take it and take it up here. CH3 minus, CH2 minus will become CH3. So eventually what is going to happen? This is going to become CHO. This entire part is going to become CHO, and this part becomes your ether, CH2O, CH2R, OC bond is there, right? So that should be the answer for this question. But this is no way that it is part of your syllabus. Okay, don't worry. Fine, next. Fine, anyways, which of the following yeah, Kana.
Sir, why can't ester be formed? The previous question.
No, ester, I don't think the mechanism will work that way. Ester has to form means this has to attack here. This C double, this RCH2O minus should attack this particular carbon atom. That will not happen. Right? Only conjugate addition would happen. Okay.
Okay, sir.
Anyways, don't worry about it. Next. Which of the following compounds can be used as antifreeze in automobile radiators? I think the answer is what? Glycol. What is it? What is the answer? This is a famous question, right? Antifreeze. Guys, answer is not nitrophenol. What is it? Can you guys check in the book? Wait.
Sir, I think it's glycol.
Sir, it came, sir. Ethylene glycol.
Where is it? Yeah, here. Ethylene, ethylene glycol or propylene glycol. Yeah, it should be glycol. Yes. Next. Monobromination of phenol occurs in dash solvents. Monobromination. Right now, if you just put Br2 in the presence of H2O, what happens? This OH is a very good activating group. It will not just stop at ortho or para position, it will take up all the positions, Br, and Br. Right? But this is not what we want. What they want is monobromination. If you put water, that's what will happen. Right? So we should, if the same thing, if you put Br2 in a solvent, not like water, but like carbon disulfide, CH2, right? At that time, the reactivity would be little lesser, right? It is going to become, say, Br in only one of the positions, or either in ortho or para, right? So it should be less polar solvent, is what you understand. Aqueous means obviously H2O, and aqueous is also highly polar. Just give me 1 second, guys. Okay, so the answer is less polar then, right? Okay, next. When benzene sulfonic acid and para-nitrophenol reduce NaHCO3, the gases released respectively are. Now we have benzene sulfonic acid, that is your SO3H with benzene ring, right? And your para-nitrophenol, OH with NO2. Okay, now it is going to react with NaHSO3, NaHCO3, right? Now this, any phenol is not good enough to react with NaHCO3, that is a weak base. They can react with NaOH. They can react with Na, but not with NaHCO3. Whereas carboxylic acids, COOH and this SO3Hs can react with your NaHCO3 also. Okay, right. So in this case, whenever this thing is going to react, it is going to form what? This is not going to react at all. That is para-nitrophenol is not going to react at all. Benzene sulfonic acid only will react to form SO2 and CO2. Where is it? SO2 and CO2. That's the answer. Okay, right. Next. And obviously the salt would be what? Salt would be sodium sulfate. Right? That's the acid-base reaction which will happen. Right? Okay, next. The gas evolved on heating CH3MgBr in methanol. Now, guys, we know that all Grignard reagents be stored under anhydrous conditions, we say. Why? Even in the traces of presence of H+, what is going to happen? The CH3 minus coming from the Grignard reagent will take up, and this is going to form CH4 gas. I know methane is a gas, right? So obviously, where is H plus coming from? From your CH3OH. I know alcohols are acidic, right? So this H plus only comes here and it reacts with the form your methane gas, right? So the answer would be methane. Okay, next. Salicylic acid is prepared from phenol. This is a very famous reaction. Raymer-Tayman reaction. So we have
can you show the before?
What kana?
Can you show the before slide?
Yeah.
Sir, gas evolved on heating, right?
Gas evolved on heating.
Sir,
Yeah, heating, right? But in this case, what is going to happen?
Sir,
Methanol is going.
Only when RMGX come in contact with water, it get converted.
No. If see, it's not because it's water. It's because water also contains some H plus. Any polar solvent is going to give me H plus. This would happen. Are you able to understand? Even in the presence, even if I make this react with your CH triple bond CH, this Grignard reagent, so-called Grignard reagent, this can come out as H plus, right? Your alkynes. They will also again give me the same product, CH4, or engender any alkane for that matter will only happen. Okay.
Sir, so by heating, how are we generating H plus?
Heating, no, they will be very close by, right? They both will be very close by. So it's like you don't have to think about, H plus coming. Say, for example, this CH3 minus is there, and then we have, say, this methanol molecule, right? Slowly this bond forms, slowly this bond weakens. Is it not? Yes.
Yes, sir.
Right? Okay. Fine. So Raymer-Tayman reaction we are seeing, right? What is it? So we have to use CH, Cl3 and KOH, and we know that, yeah.
Raymer-Tayman is used for salicylaldehyde, right?
Salicylaldehyde, yes.
But here,
Right, but we'll see. In this case, we are going to produce CHCOOH. Now, how will I put COOH here? For the same thing, if I use CCl3 instead of CHCl3, right, and in the presence of KOH, now in that case, we will be able to go for COOH here.
sir, for salicylic acid, we should do Kolb's electrolysis.
So salicylic acid, we will go for
Kolb's reaction, right?
Kolb's reaction, but
CO2.
that option is not there, right? What should I choose?
None
Then?
of these.
Why Reimer-Tiemann is happening, right? CCl3 plus KOH is happening, right? COC. The same, that is also called as Reimer-Tiemann only. Is it okay?
Sir, can you repeat?
Kana, this CHCl3 and KOH, if I put, I'm getting CHO, right? But look at what I'm putting here. Sorry, I'm putting CCl4, not CHCl3. If I put instead of chloroform, if I put carbon tetrachloride, see what I'm getting. Salicylic acid is what I'm getting, right? This is also Reimer-Tiemann reaction only, right?
Yes, sir, I didn't know this reaction.
Okay, right. This is also Reimer-Tiemann only. Okay, right. Next. Name the different reagents needed to perform the following reactions. I want to convert phenol to benzene. Now all I have to do is only one thing. What should I do? Convert only one step. What should I do?
Zinc
Yes,
is present.
zinc dust is what I need. Right. Next, dehydration of propan-2-ol to propene. I know that is dehydration. Any dehydrating agent is fine. Concentrated H2SO4 or H3PO4 or even P2O5 or this thing AlCl3, right? All of these will be able to do this process, right? But yeah, best answer would be to go for concentrated H2SO4 because everybody knows this, right? Okay, next. How do you obtain picric acid from phenol? Now look at this. What is picric acid? Picric acid, where is it present? Anybody knows? This one. What is picric acid? 2,4, trinitro, 2,4, 6 trinitrophenol. This is what is called as your picric acid. Okay, where is it present? Do you know? When you vomit, you're getting some yellow color liquid, right? And you're feeling some very, very burning sensation in your throat when you vomit, right? That is because picric acid is present in that. It's acid, not exactly an acid, but yeah, quite acidic it is, right? So that yellow color liquid in your vomit is what is picric acid. Anyways, right? So now you have to convert this to this. Okay, right. Now, if I directly go for nitration, yes, this would happen, right? All I require is that I have to go for HNO3 plus H2SO4. Now I know why, right? I don't have to do anything extra because I know this is a very, very, very highly activating group. We saw what was happening in case of bromine water, right? All the 3 positions were getting occupied. So normal nitration itself, I do, all the 3 positions are going to get occupied with NO2. That's what is going to happen, right? Not a big deal, right? Fine. Next, 2-methyl-propanol to 2-methyl-propene. Now I know this is dehydration again. Right? This is going to be dehydration again. Again, concentrated H2SO4 can be used, right? Okay. Next. Arrange the following compounds in the increasing order of the acidic strength: paracresol, paranitrophenol, and phenol. What is paracresol? OH. Any cresol means it should be CH3 or with OH. Okay, so this is paracresol, this is, and paranitrophenol, right? And your phenol. Again, guys, talking about acidic strength here, again, the best way to do is going for stability of the conjugate base, right? So we'll remove all the H plus, put a O minus, and a O minus, right? Now we know that this is going to be involving in resonance in all the cases. It is already stabilized. That's okay, right? But where it is more getting stabilized is what we need to see, right? And if you look at the resonance structure, this O minus is going to produce, negative charge here, negative charge here, and negative charge here. That means it is going to produce a negative charge at ortho and para positions. Okay. So if you have an electron with the drawing group at ortho and para positions, like in this case, I know this is an electron with the drawing group, right? By resonance, right? Now, if negative charge comes here, it is going to take it up and get stabilize it. right? But now what is going to happen in the case of CH3? When negative charge comes here, this negative charge is going to increase because I know this is an electron donating group, right? And in this case, nothing happens, right? So can I conclude that this one will get the first rank, this one will get the second rank, and this one will get the third rank, right? Because lesser charge, more stable, right? Lesser charge, more stable, and more will be the acidic strength. Right.
Sir.
Yes.
Sir, if instead of meta-nitrophenol, it was instead of para-nitrophenol, it was meta-nitrophenol, then which would be more acidic, this meta-nitrophenol or phenol?
Still you're asking between para-nitrophenol and meta-nitrophenol?
No, meta and phenol.
Still meta will be more acidic than phenol. Yes. Why not?
Okay.
Because
sir.
now in this case, it is able to do it by resonance, say it will be able to do it by minus R effect. But if it is going to be at para portion, it will still be able to do minus I effect. Might not be minus R, but not the resonance. But by inductive effect, it will still be able to stabilize it. Is it not?
Yes.
Yes. No. Okay. Right. Next question. Give the structural formula. Okay, there was another question before. Okay, write the mechanism using curved relation for the following reaction. Now that's very simple, right? H3O plus I need to add and it is going to become CH2 plus. Okay, let me show it to you. That's very simple. CH2 double bond CH2. Now comes your H3O plus there. They want to attack. Okay. Really, I think this is not a question, I guess. This is H3O plus becoming CH3, CH2 plus and H2. Okay. Fine. So where were we? The previous one. Right. H3O plus is going to look like this, right? Oxygen having positive charge. Okay. Right. Now what is going to happen is this is going to attack this particular pi bond. Okay. Now this pi bond is going to break like this. That means this carbon is going to get a negative charge, and that carbon comes and takes up this oxygen because it is having a positive charge. Right. So what is going to happen in that process? This carbon is going to have lost electron, so CH2 plus, and this carbon now has a CH2, and that has an oxygen which is having 3 hydrogens. Right. Okay. Next, what is going to happen? Obviously, now I can remove. Say this is having positive charge, right? Right. So what I can do is now I'll transfer this H plus like this. Okay, and let this take up this one. Right. So you will form CH3, CH2. No. Okay. Yeah, CH3, CH2. Then OH2 plus is what you will have. Right. Then at last, what I can do, I can remove the water molecule. So this will be gone, and then you will have a positive charge here. That's what is going to happen.
Sir.
Yes.
Sir, but in the middle structure, the second one, how do we represent the positive charge of the oxygen? Like 2 plus.
Sorry, what?
Sir, in the second structure, oxygen has 4 bonds, right? So how do we represent the positive side?
No, but that's okay. This is only a hypothetical situation. No, it was already having a positive charge, and now I have donated electrons to it. Generally, okay, telling oxygen can form only 2 bonds in a maximum 3 bonds with a positive charge. Yes, that makes sense. Yes, okay. Then I can talk about it like this. See, okay, I don't know space.
Sir, or else can we say that H3O plus is nothing but hydrolysis?
Yeah.
So H plus,
no,
H minus.
No. We can just say that this is just H plus instead of H3O plus, and we can show this now. Now this will break like that and take up the H plus to form CH2 plus, and this becomes now CH3. Is it not? Now this is the best way to show it. Yes.
Yes, sir.
Okay. Right. Fine. Next. What was that question? Okay, give the structural formula of the name of the product of the following reaction. Phenol is treated with the excess of aqueous bromine. Right? Now we know aqueous bromine. What is going to happen? OH, bromine water is going to form what? 2, 4, 6 tribromo phenol. That's the structure. That's the name, right? It will be 2, 4, 6 tribromo phenol. Right, and that is what is the structure of the compound. Right. Next. how many, show how are the following alcohols are prepared by the reaction of a suitable Grignard reagent with methanol. Right now we have methanol for sure. That is H and H. Right now we need to put some R minus MgX plus so that we are going to get these alcohols. Right now, what you understand is, say any R attacks here and this bond breaks. Okay, say we will have R CH2 because this carbon is having CH2 and that is having one O minus and that will eventually take up a H2 from OH. So how do you understand is this CH2OH, wherever you're seeing here, right, was actually coming from what? Was actually coming from your methanol, that is HCHO, right? So whatever is beyond that, that would have definitely come from where? That would have definitely come from the Grignard reagent is what you understand, right? So can I say this part would have come from Grignard reagent R and this part again would have come from Grignard reagent R. So what would have been the Grignard reagent? CH3, CH, CH3, MgBr. Would have been the Grignard reagent. And for this, it would have been cyclohexyl ring with your MgBr or MgCl, whatever it is.
Sir,
Yes.
how do we name it, sir?
Which one? What do you want to name?
Like Grignard reagent, can we leave it as like that?
No. We're not to worry about. Okay, if at all you want to name this, I can say that this is isopropyl. No, it's called isopropyl magnesium bromide. This is called cyclohexyl magnesium bromide.
Okay, sir.
Sir, can you explain this question again?
Yeah. So basically, they're saying that methanol is there, right? And you have to add suitable Grignard reagent to form these two alcohols, is what they're telling, right? Now, let us see the general reaction. If I have any RMGX and I have methanol, for example, right? Now this R minus, which is here, comes and attacks here, and this bond breaks. You will form O minus, and this would have gotten the R, right? So what you understand is, if it is methanol, this CH2OH part is coming from HCHO, and this R is coming from RMGX, is what you understand, right? So in this case, this would have come from HCHO. This CH2O should have come from HCHO. The remaining part, that is what I have marked here, this circle, would have come from R, and this cyclohexyl ring would have come from R. So what would have been the Grignard reagent? Just remove that part and put MgBr. Right? This would have been the negative charge attacking this carbon-carbon, and then the bond would have broken. Something would have happened. Right? Anyways, this would have been the Grignard reagent here, and this would have been the Grignard reagent here. That's what you understand. Okay. Right. Next. Right. Give the major products that are found by heating each of the following ethers with what is that? HI. Okay. Now that's very simple, right? Now you have to form what? We have to make sure that remember that first H plus attacks from HI, right? Then it is going to be an SN2 mechanism. Remember this. Okay. Unless and until something is going to be tertiary, we don't have to worry about your what is that? SN1 mechanism. Only if it is tertiary, if one of the alkyl group is tertiary, think about SN1. Okay. Now in this case, both are primary only or secondary only, doesn't matter, only SN2. So this will have a OH, right? Now where will you put the I is what is the question. Definitely it is going to attack your smaller this thing, right? Because it attacks like this, I minus, and then this bond would have broken. And then this would have formed the entire alcohol, and this would have formed your iodide. Is it not? So you would have formed CH3, CH2I, and this entire thing would have been OH. Okay. Now for this one, now you see this is tertiary, right? So definitely what is going to happen, this I minus, right, is going to attack your more stable carbocation. That would be this O minus breaking like this, so that I'm going to form a carbocation here, and this will come and attack here. So here you'll get I, right? And this will get your OH till this entire part. Right. And last one, anyways, this is very simple. Whenever we have your this thing, this is going to get a H and this is going to get an I, because phenol should be formed for sure. Okay, that we know. Right.
So third one.
Yeah, third one, what I'm saying is, say I have C6H5, CH2, O, C6H5. Right. Now what I'll understand is, again, say for example, this is going to, this C6H5 CH2 plus, if it is getting formed, is a very stable carbocation, right? Because resonance stabilized it is, right? So if at all you have a H here, you will make sure that the bond is broken like this, because so that you'll get a positive charge here. And then obviously the I minus will attack here only. That's what you understand. So it will be C6H5OH with C6H5CH2I would have been the product. Understood?
Sir, here, like the O and the benzene bond can't be broken, right? So that's
No,
why
that's what. O on the benzene bond cannot be broken. That is one
Sp-
reason for sure, because there's a
sp2.
double bond character.
Yes, sir.
And also you see that it is going to happen through SN1 mechanism only. That means this, there'll already be a positive on this oxygen because H would have attacked, right? And this is going to break such that this positive is going to be there. And then the I minus attacks this. Eventually you'll be getting the same answer.
Yes, sir.
Okay, right. Next. Explain why alcohols and ethers are comparable molecular masses have different boiling points. It's very simple, because in alcohols, I know hydrogen bonding is there. As simple as that. And your ethers, no hydrogen bonding, only dipole-dipole interactions, right? In ethers, only dipole-dipole interactions are there. And hydrogen bonding is stronger. That's why alcohols have higher boiling point. Okay, next. How do you convert the following? Okay, N-phenyl ethanamide. Now I'll write the structure for this first. Now we have an ethanamide. First we have C double bond O with N, that is there, that is amide. And we see that this ethanamide means 2 carbon atoms with this side. And to the N, we see that phenyl group is attached. That is, this is going to be C6H5. That's it. And obviously I'm going to have one hydrogen. That is there for nitrogen. That's okay, right? Now let us draw the structure in terms of the benzene ring. Let's say we have C6H5, we have NH, C double bond O, CH3 is what I have. Okay, right. Now I want to convert this into bromo aniline, para bromo aniline, that is NH2 here and Br2 here. Sorry, Br here, right? Now we understand that this entire part can be easily converted to the NH2 part, right? Why? Because this is an amide and I want to convert it into an amine. Now that too, we have to just break the bond like this, is it not? Right? A simple hydrolysis is enough. H2O in the presence of H plus. But you should not do it first. Why you should not do it first is because the same reason of phenol. Phenol is highly activating, and that this Br will go to all the 3 positions. You have to get only para. So first what you need to do is you have to go for bromination. That is Br2 in the presence of FeCl3 or something you'll put bromination. You'll go. So that Br will come here. After that, you'll go for hydrolysis, H2O in the presence of H plus, so that this entire part now you convert it into NH2. That's what you should do. That's very simple. Okay, right. Next, we have benzene diazonium chloride. Yes.
Sir, with para bromo aniline, what would the side product be?
What would be the
Side product, like
para?
ortho
Will be a side product.
No, sir, not that. Like ethanol or ethanoic acid.
I don't understand what.
Sir, ethanol will be formed or ethanoic acid will be formed, sir, after hydrolysis.
Oh, that one. You're asking about this one, right? Now that is going to form ethanoic acid only, CH3COOH.
Okay, sir.
Okay, because you understand here H will go, here OH will go, like that. So CH3COOH is what you'll get.
Okay, sir.
Anyways, right. Now benzene diazonium chloride to nitrobenzene. Okay. We have to convert this N2 plus Cl minus to nitrobenzene, NO2. Now there's no direct method, okay? You have to do 2 twice, right? First method will be to put H3PO4 and convert this into benzene and then go for HNO3 bar H2SO4. Right? You get nitration, right? I don't think there's any other direct method. Okay, this is the shortest I can think of. Right. Next, what I have is benzoic acid to aniline. Okay, benzoic acid to aniline. That is COOH. 2 aniline is NH2. Okay, right. Now what I can do is I can go for decarboxylation. I can go for NaOH bar CaO. If I do that, I know this entire part will be gone, right? Decarboxylation, I'll get benzene, right? And that benzene, I'll go for nitration, HNO3 bar H2SO4. You will form nitrobenzene, right? And then I'll go to this by putting SN bar HCl or any reducing agent. This is what I can do. Okay, this is minus CO2, decarboxylation.
Sir,
Yeah.
sir, here can we convert it to benzene COCl from
We can do that. Okay, then what will you do?
sir?
Oh, there is another beautiful method. Just now I thought of that'd be a very good method using a name reaction also. Look at this, guys. Say we have COOH, right? Let us make it react with ammonia, right? So what is going to happen? We are going to form C double bond O NH2 is what is going to get formed, right? Amide will be formed, right? H from this and OH from this you'll remove. Okay. Then what I can do is go for Br2 in the presence of KOH. What reaction is this? Guys.
Hoffman.
Exactly. Hoffman bromamide reaction. I know what is going to happen. This C double bond O will be gone and this NH2 will be directly attached. This is the shortest method. Yes, right. That's a good one. Right. COCl. Okay. After COCl, what will you do, Gana?
Sir, I meant this reaction only, sir. But
Oh, you meant this only, but you can, instead of going for COCl, you can directly go for CONH2.
okay, sir.
And then do the bromine, this thing, Hoffman degradation. Right? Okay. Right. Next. How would you synthesize the following alcohol from appropriate alkenes is what they're asking. Right now, that's very simple, right? Remember that whenever I go for alkenes hydration, right, I have to go for Markovnikov's generally, right? So I would have had a CH3 and I would have had alkene like this, and I would have had H3O plus, obviously carbocation would have formed, and OH will go for more stable carbocation. OH will come here only, right? For this one, it's very easy, right? All I have to do is put a, now I have, okay, I think this, the OH should be here. Okay, fine. Anyways, all I have to understand is I put a double bond here. Now this is symmetric. However, you can do it, right? Now this one cannot be symmetric. You have to put the double bond, right? You have to, if you put the double bond here, that's okay, because again, Markovnikov solution will give me here only. And if you put it in this way also, it will come here or here only. Anyway, that's going to be fine, right? And for this one, right? Now, if you have something like this and we have a methyl group, now please understand you cannot put the double bond here wherever I'm marking, making it dark, right? Because if you do that, oh, in that case also you'll get OH here only because this is tertiary. Yes, you can put it here also, or you can put it between these two carbon atoms also. That is also going to produce the same OH only if we go for hydration. Okay. Next. Give the chemical test to distinguish between phenol and ethanol in seemingly condition. Ethanol is containing CH3CH2OH and phenol is C6H5OH. And then I can easily do it by iodoform test. Why? Because iodoform test, you can generally we say that we require the CH3C double bond O. This group is required. But what you understand is the reagents, that is your NaOH plus I2, is going to form something called as NaOI, sodium hypoiodide. And this is a oxidizing agent also, right? So what is going to happen is this will be converted to CH3C double bond OH, and now you see that there is a C double bond. So even alcohols capable of giving this particular aldehyde or ketone on oxidation and which contains a C double bond or CH3 will also give iodoform test, right? So the first one, iodoform test, would be the answer. Right. Next, write the chemical equation for what happens when tertiary butyl alcohol is treated with reduced copper and burnt what tertiary butyl alcohol with 573 and copper. Now we know what reaction is this, right? Right. Tertiary alcohols on heating with copper is going to give you what? Alkene. Right. Primary alcohols will give me aldehyde. Right. Secondary alcohols would give me ketone. Right, and the tertiary alcohols will give alkene. Now you're talking about tertiary butyl alcohol, that is this C with the OH here is what is tertiary butyl alcohol. Now with this on heating with copper and heating is going to form what? C and double bond C, and you can put the double bond anywhere, here or here. Both will be same thing only. Okay, that's the answer. Right. Next, give equation only to distinguish between primary, secondary, and tertiary alcohol by Victor Mayer test. Do you have Victor Mayer test in the syllabus?
No, sir.
No, don't worry about it. Okay, next.
Sir, we can do it Lucas test.
Yeah, locus test we can do. That's easy. Okay. And I think we are done. Okay, good set of questions this was, right? It was very interesting to solve. Okay, any other questions you have, guys?
Sir, here for the first subdivision, sir, when this type of questions is given, can we convert that component to some other thing and then
No. You have to take only tertiary alcohol with copper. That's a direct reaction you should write. That's it.
no, sir, the distinction test. Like,
Distinguishing.
if
No.
I
You
write-
cannot do that. No. You cannot convert that into something and then tell that that is possible. No, that you cannot tell.
Okay, sir.
Okay. Fine. Was it the question paper today or was it just the syllabus sheet? I mean, the revision, this thing, this is?
Revision, sir.
This is revision only. Okay. Fine. Anyways, a good paper it was, except for some questions out of syllabus. That's it. Okay, guys. Thank you so much. We'll meet again.
Thank you, sir.
Thank you.
Thank you.